Bismillahirrahmanirrahim. Today we'll be solving chapter question 2.11. I'd already made a video on this, but there I followed the solution manual primarily, which did not make sense. When a student asked about what to do for delta-delta connection, then I had to research and find out in an easier method. So today we'll discuss that method by which you can solve all types of questions. So let's see. We have learned already that the approximate transformer model could be either referred to primary or referred to secondary. And this is called the excitation branch resistance impedance. And this is called the series resistance and impedance. And a simplified model is that we remove this branch and this becomes a simplified model for primary and secondary side. The question that we are dealing is in per unit. So for per unit, we'll be using this formula. That means the left side will be V per unit, and right side also it will be Vs per unit. And the current is Is per unit and IP per unit, although they are same current because they are flowing on the line. Let's see the question. Now this is the question. Long question, so I'll not go through this, but we'll go one at a time. So let's move to the next slide. Okay, the first part. First of all, the question: 100 MVA, 230, 115 kilovolt Delta-Wye three-phase power transformer has a per unit resistance and per unit reactance, and the excitation branch elements are this and this. If this transformer supplies a load of 80 MVA at 0.8 power factor lagging, draw the phasor diagram of one phase of the transformer. First, let's see what does this represent actually. So it's a delta on the primary side and Y or a star on the secondary side. Power, we know both sides of the transfer, it remains same, so 100 MVA, 100 MVA. This is always line voltage. The line voltage is VLP on the primary side, and the line voltage VLS is 115 kV. Both are in kV. So the first thing you have to keep in mind that whenever you are solving a three-phase question, it is better to solve three-phase question by using single phase or one phase technique. And for single phase, we need only the phase voltages. So let's see what is the phase voltage on the primary side or the delta side. This is the line voltage between line to line. And this is also the phase voltage. That means in delta, V line is equal to V phase. What about Y? Okay, so this is 230 is the V phase and V line both. Now in the Y connection, it is not the same. This is the line or the line to line, and this is phase. And the relationship is that V phase is obviously less than line. It is V line divided by under root 3. So in our case, it will be 115 kV divided by under root 3. That means 66.40 kV. So this voltage here will be 66.4 kV. So these two phase voltages we have found. And now the single phase circuit could look like this. We have the single transformer. The primary side is 230 kV, the secondary side is 66.4 kV, and since we are considering only one transformer of the three phase is actually consists of three transformers, so the power will be divided. So that means the power will be 100 MVA divided by 3, that means 33.3 MVA on the primary side and 33.3 MVA on the secondary side. And the load will also divide. The load here is 80 MVA at 0.8 power factor. So that will be also divided by 3. So it will be 26.67 MVA, and the power factor will of course remain same. And then we can go for the equivalent circuit diagram, and we'll plug in the values. Now what value per unit resistance? 0.15. So this is 0.15 pu. Reactance 0.06 pu. So this is, and the excitation branch RC is 100 pu and XM is 20 pu. So this is our single phase equivalent circuit. Okay, now to the question. If the transformer supplies a load of 80 MVA, 0.8 PF lagging, draw the phasor diagram. So we have to draw the phasor diagram for one phase. And as we have already discussed, that this 80 MVA will now become 26.7 MVA at 0. This. Now the phasor diagram, for drawing phasor diagram, we will remove the excitation branch to further simplify. So just we have removed. So this is our simplified circuit with no excitation branch, and this is also referred to the secondary side. Now, and the load, as we mentioned, is this load. Now the phasor diagram looks like this. This is the line voltage. This voltage is line voltage, we are calling this, line current, I'm sorry. This is the line current. Then we take the output voltage, we are calling Vs as reference. So this is the reference with zero angle. And from here, we draw the voltage drop here, which will follow the line current because of resistance. And then we also draw the voltage drop in the inductance or reactance. So it will be 90 degrees from the resistive component. So this is ISXEQ, and the sum of all three will give us the input voltage VPU. So this is what we need to draw, but we have to find their values. So first of all, let's find ILSPU or ISPU. We'll call it ISPU. Now the ISPU, we are talking of now this region, and this is the power we are supplying. So power divided by voltage will give us the current. So IS, not ISPU. IS is load, this load 26.7 MVA, and VS is 66.4 kV. This voltage is also here, 66.4 kV. So IS will be 402 ampere. Now we have to find it in PU. For that we need the base current. And the base current is always calculated from the rated power. Now this was the load power. Our rated power here is 33.3 MVA. So we'll calculate the base current, 33.3 MVA as base, is the power base, and the voltage is of course same here, 66.4 for the time being because there is no load. So it is 66.4 kV, and the current is 502 ampere. And we have learned earlier that to find PU, we divide the actual value divided by the base value. So 402 divided by 502. So ISPU is 0.8. Now we have to find its angle as well. Power factor lagging, the cosine of 0.8. Power factor is 0.8. And for lagging, we'll use the minus sign. So this will be minus 36.87, this one. And so ISPU 0.8, angle minus 36.87. That means we have found this. So we'll just plot it here. This we have plotted, and the magnitude is 0.8 minus 36.87. So this one part we have plotted. Now let's move. So we were here. And now we can use KVL equation from this. So minus VPU plus I into R plus I into X and plus VS VPU. And from here, we will find VPU. We just take it on the other side. So this is our equation number 1. So we have to solve this equation to find VPU. And also from here, we'll find this voltage. And from here, we'll find this voltage. So let's first of all find VSPU. Now VSPU, we take this as a reference, and generally it is taken as 1, but there is a way to find out, and that is that VSPU is Vs over V base. Now in this region, the transformer actually divides the base region. So here the Vs is 66.4, and the same Vs is also our base voltage. So that is also 66.4. So dividing, we get 1.0 pu as our Vs. And now we'll plug in the values. So we have this as 1.0. This current 0.8 minus 36 point this R was 0.015 pu, and similarly for X terms. And now multiplying these, we get these two terms. Now, as I was mentioning, this is representing this current. This is this voltage here, negative side. This is representing this voltage, and 1 is of course the VSPU. Solving this, we find VPPU. This one here is 1.039 angle 1.07. And so we can now write the values. Vs is 1.0. This one is, as I mentioned, 0.12. This one is 0.48. And VPU is 1.039. So this is our phasor diagram, part 1 of the question done. Okay, let's move to the next part. Now, this diagram I have drawn in the book. He has drawn this diagram in the solution manual, actually. So this is a shortcut. What he has done is he has taken this reference, and then he has drawn this VP and connected these two. And this is the current. But I prefer this one because here you get exact feeling that what is happening. From the reference, you are dropping in the resistance, so you go following the current, and then this will be 90 degrees from there, so you going here, and then you connecting these, you find the output. That comes from here. If you see Vs plus ISRE plus ISXE, and this gives you VP. Anyway, let's move next. Part B is, what is the voltage regulation of the transformer bank under these conditions? Now, this formula is used for voltage regulation when the items are in per unit. So we'll just follow this. And we have everything here. VP, this is VP 1039. This is Vs, which is 1. And so plugging in the value, so 1.039, 1 and 1 percentage, so 3.9% is the voltage regulation. Then part 3, sketch the equivalent circuit, refer to the low voltage side of one phase of the transformer. Now low voltage is our, the secondary side actually. Calculate all transformer impedances, refer to the low voltage side. So what basically is saying that all these values that we have in PU, we have to convert them into ohms. And for that, okay, what are in ohms? That is the question. So for that we need Z base. Now this is the formula. We have ZSPU. These values are given. We have to find Z equivalent in ohms. So we can say Z equivalent in ohms is equal to Z base into ZSE. ZSE is given, Z base we have to find out. And how do we find that out? This is the formula for Z base. The V base square divided by S base. And what is V base in this case? This is the diagram. You can see it is 66.6 and S base is 33.3. We'll use that 66.640 kV square divided by 33.33 MVA. So basically 66.40 divided by 33.3 kVA square is actually becoming or K square becomes M. So that is why we don't have to bother about this. So this answer is 132.27, which can approximate it as 132 or 133. In the book he has given 133, so I'm taking that. So Z base is known. And now we can find all the parameters. Now this is given. Note down everything. So R equivalent is 0.15 multiplied by Z base. This formula we are using. It is 2.00 ohm. Similarly, X 0.6 PU 133, 7.98. RC is 100, 133, 13.3 kilo, and XM similarly 2.66 kilo. So this is the answer for part C. Now part D is saying determine the losses in the transformer and the efficiency of the transformer under these conditions of part 2. Now these parameters we have already calculated, so we'll now calculate the loss. So for the single phase circuit, the actual loss in the series resistance is R or PR is equal to S base into PRQ. Just similar to this formula that we are using. ZEQ is Z base into ZSE. Similarly for power. Now remember, power and S are same. S is the apparent power and P is the what called power in, or the real power in watt. So we want to calculate the loss in watt. We'll multiply S base by PREQ. So let's find out PREQ. Now PREQ, that is the drop in the resistance. Drop in the resistance is I square REQ or IS square R, we know. So we have already IS. So now from here, this is our S base, 33.3 MVA into I square R. I is 0.8, 0.8, and REQ is 0.15. We are only taking the magnitude. So this is the loss in the series resistance here or here. Similarly, now since we are calculating the loss in watts, we are only concerned about the resistance, not the reactance. So the actual loss in the excitation resistance is same formula, except that the resistance is 100 pu. And since this is in parallel, we will calculate the V square over R formula. We'll use the V square over R formula or VP square over R formula. So this is 33.3 and VP is, we have found already, it is 1.039, using that square and divided by this resistance of 100 pu. So this is 0.36 megawatt. Now this is for one phase. So if you want to know the total, then you have to multiply by 3. It will be total loss in the transformer, because that is what is asking, the losses in the transformer. So we have to multiply these losses by 3. So this is the total loss in the series resistance. and this is the total loss in the excitation branch resistance or parallel resistance. Then there is another part that is called the find the efficiency of the transformer. So efficiency formula is this one, that P out over P in into 100. We can find this by the single phase as well, but it is better that we find it for the total overall. So let's see that now. The P out and P in can be written as P load, that is drop in the load, then drop in the resistance, and the drop in the reactive part. Okay, now the load, total load was 80 MVA, so we'll use that because now we are using the efficiency using the total transformer. And PR equivalent was 0.96 megawatt and PEX was 1.08. This is not for the reactance, this is for the parallel branch. Actually, we had calculated. So 80, and this is also P load 80, 0.96 from here and 1.08, and dividing, the efficiency is 97.5%. So I hope you have been able to follow this. Please let me know through your comments. Thank you.